So the next very interesting chapter, actually my favorite chapter in the whole of theory of computation, are the concepts of undecidability and computational classes, right? Again, the concept of computational classes and undecidability have very real world implications, right? This is not some blunt mathematical theory. This has tons of real world implications that we will learn of by the end of this chapter, right? So we have seen what undecidability is briefly, right? Even earlier. But broadly speaking, what we'll try to do in this chapter here is we'll try to see problems which are undecidable, right? For example, we have discussed of things like halting problem, right? We've discussed about halting problem in the very first introduction video of theory of computation itself, right? So we'll discuss about halting problem much more formally enough. Again, till now we have already learned what a Turing machine is and what are regular languages, what are context-free languages. We have learned about languages, grammars, and we've learned a lot about Turing machine itself. So most of what we will learn or what we'll focus on in undecidability and computational classes will be around the concept of Turing machine itself, right? For example, let me ask you some interesting questions to motivate this discussion, right? The first and foremost is, can you tell me a language? Can you tell me a language that is not recursively enumerable? That is non-recursively enumerable language. Because we've seen lots of languages till now, right? We've seen lots of languages when we learned about context-free languages, regular languages, etc., etc., etc. Even context-sensitive languages, we have seen some examples, right? Can you tell me a language which is non-recursively enumerable? Similarly, can you tell me a language which is recursively enumerable, but not recursive? Can you tell me some languages like this? Again, we'll start this whole undecidability discussion by focusing on languages like this, and then we'll go into some problems which are not decidable, right? Again, when we learn about many more concepts like what is reducibility, etc., right? So a very important, very core concept. Reducibility is a very important concept both for undecidability and computational classes. And as you progress through a lot of these concepts, let me also just give you a note here that some of these concepts are deep, right? Some of these concepts are deep and they might be slightly tricky for you to get it the very first time, because their flow of logic or the flow of arguments that we will make, very logical arguments, can be slightly tricky the very first time you say it. So some of these concepts, for many students, you might have to watch it maybe twice or even thrice in some instances to be able to completely absorb this concept. Again, to be honest with you, when I learned undecidability in my undergraduate days, even in my graduate days, right, even in my master's days, this was one tricky concept. I never got the concept the first time I read it, even from the best of books like Hopcroft Ullman. I had to read it twice or thrice to be able to completely absorb what is happening, right? So you will encounter these issues for this concept, especially undecidability and computational classes. Some of these concepts are deep and it's tricky to get it the first time. So please be patient. You might have to watch some of the videos in this chapter multiple times to be able to completely absorb the concept, right? At the same time, I told you about real world implications, right? So in computational classes, we will learn about things like NP complete, NP hard, right? The whole class of problems, NP hard and P, right? So we will learn of these problems, and these problems are very important, or these concepts are very important for day-to-day algorithms. So there are a lot of important real world algorithms problems which fall in different classes of NP complete, NP hard, or P. Depending on where they fall, we can guarantee, or we can make some certain assertions about their time complexities, right? So what we learn in undecidability, especially in computational classes, has lots of implications for real world algorithms. Again, if you recall, in our algorithms course itself, we did not go into NP, P, etc. in lots of detail, primarily because I needed the concept of undecidabilities and Turing machines to be able to rigorously and formally explain these concepts to their core ideas, right? So with all of this, let's go. Again, I will try to keep these videos very simple to understand, but please realize that you might have to watch them multiple times, and I'll try to break this into individual concepts, and I'll connect each of the concepts one by one as we progress through this chapter. Okay, the very first thing that I want to discuss about is, can you encode a Turing machine? What is a Turing machine? Think about it. What is a Turing machine, right? In the case of a Turing machine, I have an alphabet of input symbols. I have a bunch of states, right? I have my tape symbols. I have my initial state. I have a set of final states, right? I have right and left directions, right? I have right and left directions, and I have a transition function. Broadly speaking, these are what constitute my Turing machine, right? These are what constitute my Turing machine. And of course, there is a special symbol called a blank symbol, obviously, right? So if you notice, if I want to encode a Turing machine, suppose if I want to encode a Turing machine using binary strings, right? Using binary strings. If you think about it, most computers actually store everything in binary, right? Computers, whatever file you give, whether you give it a music file, whether you give it an image, whether you give it a video, whatever you give, at the end of the day, everything is encoded into binary, right? A computer only understands binary. You might have learned this in your computer organization, digital logic circuits, etc. Everything has to be in binary. So similarly, can I encode a Turing machine into binary strings? Right? There must be some way to encode it, right? Because I can encode anything into binary, literally. Any information that is available, I can encode into binary. So we'll look at one encoding of Turing machine. And again, right now what we're learning is a simple concept of encoding a Turing machine using binary strings. But this concept is extremely important. This concept is super duper important for many problems in undecidability that we will learn of, including these problems. Right? So first let's go again. Think of this as a basic concept that we are learning. We'll build on top of this concept in the next few videos. Basically, what I'll do here is this. Okay. So let me come up with some rules or guidelines. Right. So first I'll assume that the states in my set Q are Q1, Q2, Q3, etc. So let's assume the default Q1 is the initial state. Right. I don't have Q0. And again, you will understand why I'm not taking Q0 in a little while, right? So I can always construct a Turing machine like this, right? So given any Turing machine, I can map it into this type of format. I'll call Q1 my initial state. I'll call Q2 my final state and the only final state, right? I'll call my Q2 the final state. And given a Turing machine with multiple final states, we can easily convert it into a Turing machine with a single final state. We can easily do that. Then let's assume I have other states. Let's assume Q3, Q4, because I could have multiple states in the finite control of my Turing machine, right? So let's assume all these states, I'll just call them as other states. Remember, please note that there is no Q0 here, and that's by design, right? So now if you look at all the symbols that I can have both on my tape and input symbols that I can have, my tape alphabet and input alphabet, I'll give some special indices here, right? So I will call X3 as my blank symbol. Look at this. I'll call X3 as my blank symbol, right? Let's assume I call X1, X2, X4, X5. All these are other symbols that are either part of my input alphabet or my tape alphabet, right? So these are other symbols. These are other symbols that I can encounter. Again, you might wonder, why did I choose X3? I could have chosen any X here, to be honest with you. I could have chosen X1 as my blank. I could have chosen X2 as my blank, but you need to fix one Xi uniquely for your blank, because blank is a special symbol, right? As far as your Turing machine itself is concerned. Rest every other symbol that you can get either as an input or as part of your tape alphabet, let's just call them as X1, X2. If you notice one more thing here, there is no X0, and that's by design, right? There is no X0 here. If you notice here also, there is no Q0, and I'm doing it by design. I'll tell you why everything fits in here, right? Now imagine I have two directions, right? Left and right. I have two directions. I will call left as direction 1. I'll call right as direction 2. Okay. Again, remember, I'm giving some numbers to them. I'm giving some indices. Again, if you notice, there is no D0. Intentionally, I'm not using zeros here. And there's a very important reason for it that we will learn of very simply, right? In just a few minutes, you will learn of it. What is the most important part of a Turing machine? The most important part is basically your transitions. If you encode all the transitions, look at this. If somebody gives you the transition table or the transition diagram of a Turing machine, you can easily decipher what are the states, what are the input symbols, what are the tape symbols, what is the initial state. All of that you can easily get if somebody just tells you the transition function. Again, given the fact that I'm always assuming that my initial state is Q1, Q2 is the only final state, my directions are also encoded using numbers. So if you think about it, imagine if I have a situation like this. Imagine I have a imagine if I have a transition. Imagine if I have a transition like this, right? So Qi from state Qi on input Xj, right? This is the input symbol that I'm seeing on my tape right now. This is my current state. Then let's assume I replace this Xj with, let's say, XL, and I go from state Qi to, let's say, Qm, IJKL, right? And let's assume the direction that I'll move is DM. Look at this. I'm putting indices here, right? So now let's go through this. How do I encode this single transition? Remember that this is a single transition. This is a single transition, right? So I'll just explain you how I can encode this single transition. It's actually very simple. Now, if I can write this as a 5 tuple. If you think about it, I can write it as a 5 tuple. Qi, Xj, Qm, XL, DM. Now, if you notice, Ij in this I, J, M, L, and okay, so I should actually write this as, so let's call this as K instead of M, right? I, J, K, L, M, right? I should call this as K because M is already used here, right? So let me just call it as I, J, K, L, M. So I, J, K, L, M, all of them are strictly greater than 0 because of the way I've defined everything here. Look at this. There is no Q0. So which means I will always be greater than 0. There is no X0, which means all J's will be greater than 0, right? There is no D0, which means all of them will be greater than 0, right? Now, to encode this as a binary string, what is the simplest way to encode this as a binary string? Let's see. So I have I here. If you just tell me the index, I'm good. So what I'll do here is, so I'll write this, I'll encode this as a binary string as follows. This is the most important step. I'll write this as 0 power I. I'll repeat 0 I times to encode Qi. Then to separate Qi and Xj, I'll place a 1 here. This 1 you can think of it as this comma. Think of this comma being replaced by this 1. Then I have Xj. Xj, the most important thing here is the J, the index J, right? So I'll write this as 0 power J. I will write this as 0 power K. I will write this as 0 power L. I will write this as 0 power M. Look at this. My 1 is being used as a delimiter or a separator. So if somebody gives me this binary string, look at this. If somebody gives me this binary string, I can easily arrive at this 5 tuple. The moment I arrive at this 5 tuple, I can arrive at this single transition, right? So this is a way to encode a single transition. But a transition function has multiple transitions. How do I encode multiple transitions? Very simple idea. If you notice here, because I, J, K, L, and M, all of them are greater than 0, you will never have a situation where you'll get 2 1s side by side. So what I'll do here is I'll place 2 1s here as a delimiter between 2 transitions. This is my first transition. This is my first transition. This is my second transition, right? Look at this. This is just one transition, right? Your transition function has many transitions like the first transition, second transition, third transitions, etc. So each of these transitions I'll represent using this, and the delimiter between, so this is the delimiter between, this is the delimiter or the separator between 2 such transitions, right? Very simple idea, right? Now imagine if somebody just gives me this string. What is this? If you think about this, this is basically a string of 0s and 1s, right? What is this? This is basically this whole string that I got, right? This whole word that I got. This word belongs to 0 plus 1 star, right? This is basically a string of 0s and 1s. That's all it is. Of course, there is a specific format behind this. The moment I start reading, look at this. I always start with 0. The moment I see a bunch of 0s, I'll interpret this as Qi. Then when I look at 1, I'll say, okay, this is delimiter. Then I start counting my J's. So I start counting my 0s. That will be my J. Then 0 is the delimiter. Then I start counting 0s. That will be my K. This will give me QK. Similarly, I'll get XL. I'll get DM. Now, from this string, I got this 5 tuple. From this 5 tuple, I can get the single transition. Now, the moment I encounter two 1s here, I know that, okay, this transition is done. The next transition is starting. Right? Again, I'll interpret the second transition just like this and I'll get it. Right? So this again, there are many ways you can encode a Turing machine using binary strings. This is one of the most popular ways. Right? So if you think about it logically, You can think of a Turing machine as a binary string. You can think about Turing machine itself as a binary string, because I'm able to encode all the information that is there in a Turing machine. All the information that is in a Turing machine, I can encode it just using a binary string, right? So the moment I can represent a Turing machine using a binary string, I can interpret this binary string as a binary number. Given any binary string, I can read that as a binary number, right? Or base 2 number. Given any base 2 number, I can read it as a decimal number. I can read this as a decimal number. I can convert from binary to base 10, which means now I can start talking about 0th Turing machine. Now I can start using terms like this: 0th Turing machine, first Turing machine, second Turing machine, right? I can start talking of things like this, because what I mean by second Turing machine is take 2 in decimal, convert that into binary. What is the binary equivalent of it? 1, 0. Now this binary this binary number represents a binary string. Corresponding to the binary string, there is a Turing machine, right? So I can start talking about Turing machine I. What does Turing machine I basically means? Take the I, look at this I. This I is a decimal number. It's an integer. So think about it as a decimal number. Given this I can convert it into a binary number. I can now interpret the binary number as a binary string. Corresponding to this binary string, there is a Turing machine. But here comes a challenge. Not every binary string, look at this, not every binary string is a valid Turing machine. Not every binary string is a Turing machine. So let me show you why. Suppose if I have a binary string like this, 11001. Suppose I have a binary string like this, right? If I try to interpret this as a Turing machine, what should I do? I'll start from the very first. If you look at how we have encoded the Turing machine itself as a string, it should always start with zeros. First, I should start with zeros, then some 1. I should have this whole pattern here. But if you notice, this is starting with 1, which means there is no Turing machine that is equivalent to this, right? This is not a valid Turing machine. This is not a valid Turing machine. For all such strings, again, if you look at this is also not a valid Turing machine. This code, because it's starting with 1 here, it doesn't correspond. It's not a valid Turing machine binary string, right? So now can we fix this somehow? The fix that we say here is this: if there is any number, so take number 2. Take number 2 in base 10. This is 1, 0 in base 2, right? If I interpret it as a binary string, this is 1, 0. But this is not equal to any valid Turing machine. This is not equal to any valid Turing machine's binary encoding. Not equal to any valid Turing machine's binary encoding, right? Because this is starting with 1. Because this is starting with 1 here. Then what do? Can I create a Turing machine corresponding to this? I can. So what I'll do here is, if the string itself is invalid, I'll create a Turing machine. I'll create a Turing machine with only one state. Okay, I'll create a Turing machine with only one state and no transitions. So I'll create a Turing machine like this. No transitions, no final states. So let me write it as Q1. No transitions, no final states. So this is my Turing machine. What happens to this Turing machine? What is the language accepted by this Turing machine? The language accepted by this is the null language or the empty language. So if I ever encounter a invalid Turing machine encoding in my binary string, I can define a Turing machine for this, which is the Turing machine that accepts no words, right? Now I can talk about, okay, so what is my second Turing machine? My second Turing machine will look like this, and the language accepted by it is the null set, because 2 represented as a binary string is not a valid encoding as far as this structure is concerned, right? Now I can say 0th Turing machine, first Turing machine, second Turing machine, kth Turing machine. Either if k is a valid, if k, which is in decimal, when I convert into a binary string, if it's a valid binary encoding, perfect. There is actually a Turing machine corresponding to it. But if it is not a valid binary encoding of a Turing machine, it will correspond to a Turing machine like this. All invalid Turing machine encodings, as far as this strategy is concerned, we will think of them as a Turing machine like this, where there is an initial state. My initial state is Q1. There are no transitions out of it, right? And no final states. So this Turing machine accepts the empty language, right? So now I can start talking about Turing machine I. So now for every I can say Turing machine 0, Turing machine 1, Turing machine 2. I can start talking about Turing machine with some index associated with it. Because of this whole encoding strategy, because of all of this encoding strategy. Again, this is useful. We'll see why this is useful in the next video. But I hope you understood how to encode a Turing machine using this strategy. Again, this is slightly tricky to grasp the very first time, but once you get a hang of it, it's very, very simple. And the reason, again, this is very important. Why we didn't use Q0s, X0s and D0s? Because I don't want two ones here unless it's a delimiter between two transitions. Imagine if L was 0, let's assume. If L was 0, 0 power 0 is epsilon, so I'll get two ones here. I don't want that. Within a single transition, when I'm encoding a single transition, I don't want two ones together. That's why I avoided Q0, X0 and D0. Right? Again, please remember that this is a very foundational concept of encoding a Turing machine as a binary string and interpreting a decimal number itself as a Turing machine and talking about Turing machine 0, Turing machine 1, Turing machine 2, etc. This is very, very important concept, right? We'll use it very soon in the next few videos.